My name is Professor Duke Orata. We are continuing with our lecture series in thermodynamics. Today we look at the efficiencies for Rankine cycle and Carnot cycle. We just remind ourselves, let's go back to Carnot cycle. We said that Carnot cycle had four processes. We have the isothermal expansion, we have the adiabatic expansion, isothermal compression, and adiabatic compression, and that is in the pressure volume matrix. And we had mentioned that for us to customize Carnot cycle in the Rankine axis, that is where we are talking of temperature and entropy as opposed to pressure and volume, then we'll have to use, instead of using an ideal gas, like we had said in earlier lectures, an ideal gas obeys the equation PV is equals to nRT, which is the equation, ideal gas equation or equation of state. We said that we'll have to replace that fluid in Carnot cycle with water or steam so that we are able to customize it on the Rankine axis, that is temperature versus entropy. And so let us just draw the Carnot cycle in the Rankine axis. So we have temperature and we have entropy. So that for the Carnot cycle, of course, we have this is the saturated vapor curve, and this is saturated liquid curve. So we are saying in the Rankine axis, we will have for the Carnot cycle that kind of a profile. Can have that kind of a profile, or we can have also that kind of a profile. So we have 1, 2, 1, 2, 3, 1, 2, 4. So we have the Carnot cycle. And the other one where we have 1, 2, 3, 4, 5, 6, that is the Rankine cycle. Now, we had said that for us to work with the Carnot cycle in the Rankine domain, then it means that one, we have to realize two things. So let's just remove the Carnot component and just remain with the Rankine, the Rankine component and remain with the Carnot component. We say that we realize two things. One, the Carnot cycle, the process 1 to 2, which is isothermal. The process 2 to 3 is adiabatic. 3 to 4 is isothermal. 4 to 1 is adiabatic. Now, remember when you talk of adiabatic, the process 2 to 3, this is an isentropic process. It's an isentropic process. In other words, the entropy is constant. And from Clausius inequality, we say that ds is greater or equal to dq over t. So under constant pressure, ds is greater or equal to dq pt. And that is heat transfer under constant pressure, which is enthalpy. And we are saying that because the process is isentropic, ds is 0. So that dq is also 0, so the process is basically adiabatic. So steps 2 to 3 and 4 to 1 are adiabatic as much as they are isentropic. In other words, there's no change in entropy. Now, like you have said, we need to use water in place of ideal gas to customize the Carnot cycle into Rankine cycle. Now, the other thing we realize is that this constant temperature, let's call that TH, temperature of the hot body, TC, temperature of the cold body. And you remember from our earlier discussions on Carnot cycle, we had said that CV dt over T, the cyclic integral, is equal to the cyclic integral for dq over T plus the cyclic integral of nr dv over v. And the cyclic integral, we said, consisted of 4 line integrals, so that we have CV dt for process 1 to 2, CV dt over T for process 2 to 3, CV dt over T for process 3 to 4, and CV dt over T for process 4 to 1, and the same goes for dq over T and nr over dv. And we saw that this quantity vanishes, is 0. Similarly, that other integral also vanishes, so that you are left with the integral, cyclic integral of dq over T, which you have said consists of 4 line integrals, that is from 1 to 2, CV dt over T plus integral of 2 to 3, sorry for that, dq over T plus integral from 3 to 4, dq over T plus integral 4 to 1, dq over T. And of course, as we had seen that time, we were able to handle this very easily, in the sense that for the adiabatic process, 2 to 3 and process 4 to 1, they vanish. 2 to 3 vanishes, 4 to 1 vanishes. So that, what are we left with? We are left with the cyclic integral dq over T is equals to q h over th plus qc over tc. Remember, h represents highest temperature and C the lowest temperature. When we remember the reservoirs which we talked about, the hot body and the cold body. And then the other thing which we mentioned is that in this Carnot cycle interposed to the Rankine cycle, then those steps where we had an isothermal process must be associated with a phase transformation. So what does that mean? If we look at phase equilibria, let's to illustrate that, let's just consider a pressure temperature diagram for, say, water. So we have our solid, we have our liquid, we have our gas. Those are the 3 phases. And of course, we have the triple point, what we call the triple point, responsive pressure of about 0.06112 bars, something in that range, very small pressure, and there's a corresponding temperature. Now, when we are dealing with these phases, that is solid, liquid, gas, so this is the pressure at the triple point, some value there, 0.6 bars, something like that. At the triple point, we have the solid, liquid, and gas coexisting in equilibrium. So according to phase rule, which is F is equals to C minus P plus 2, where C is the components, P is the number of phases, and 2 is temperature and pressure. So we see that at the triple point, where we have the 3 phases in equilibrium, the phase rule, which is F, and this is the variance of the system, or sometimes referred to as degrees of freedom, will be given by, we have 1 component minus 3 phases plus 2, so that is 0. So what does that mean? It means when you're at the triple point, you have no choice. The pressure is that, and the temperature is that. And that's why triple point is being used as a reference point in some of the temperature measurements. Serves normally as a reference point significantly because it's invariant. The degrees of freedom is 0. Now, what about if you are moving, if you you are between the liquid and gas phase? Now, this curve here between liquid and gas is where the chemical potential of that species in the liquid and gas is the same. So we write that chemical potential of that species in the gas phase is the same as the chemical potential in the liquid phase. That's along this line. And notice that if we pick pressure P1, for example, then that will correspond to a temperature T1. So the moment you have chosen the pressure, we have fixed the temperature. If you fix it at P2, the temperature must be T2. So in terms of phase rule, F in that case is equals to 1 minus 2 phases in equilibrium plus 2. So you have 1. So you have only 1 degree of freedom, or the variance in 1. In other words, if you choose the pressure, temperature is fixed. If you choose the temperature, the pressure is fixed. And so when we have phase transitions, normally the temperature is constant because you are doing it at some pressure. So that temperature is fixed at that particular point. And so that's what we are saying, that those points corresponding to isothermal processes must be mimicked or represented by phase transformations. Because during the phase transition, the temperature is kept constant. So here we will have the vaporization process, because we are at high temperatures, and here we will have condensation. Vaporization means we are moving from liquid to gas, and condensation is we are moving from condensation, we are moving from liquid to solid or vice versa. Very, very important to note that. And then the other thing which we had said is that to customize this kind of cycle into the Rankine domain, then these processes must take place in the elements which we are described in the Rankine cycle. And if you remember, we need this expression, let's leave it there. If you remember, we said that for the Rankine cycle, the elements were very simple. We had the boiler, we have the pump, we have the condenser, then we have the turbine. So we are saying that in this Carnot cycle transposed on the Rankine cycle, then the process 1 to 2 must take place in the boiler. The process 2 to 3 will take place in the turbine. So that one will take place in the boiler, 2 to 3 will take place in the turbine, 3 to 4, that's condensation, will take place in the condenser, and 4 to 1 will take place in the pump. So now let us look at the efficiency of the Carnot cycle. So always remember those diagrams. As much as I'm erasing them, they should not be erased out of your mind, because we are referring to them back and forth. So what is efficiency? We know that efficiency by definition is work output over work inputted. Very important for us to know that. And so for the Carnot cycle, remember we said we had a hot body, we have the heat engine, we have the cold body, because work is done here, heat is released there, and heat is discarded here, minus QC. So du from first law of thermodynamics for non-flow processes, du is equal to dq plus dw. And we say that for the cyclic process, du is 0. Process is cyclic. So it means that dq is equal to minus dw. And so in terms of efficiency, we are saying that will be work output, which will be minus W, you can see in the scheme there, and work inputted is QH. So don't worry if you're using Q, small q and capital Q. We are referring to heat. There's nothing different there. So that should not worry you unnecessarily. So that is the efficiency. Now, we know that for the Carnot cycle, like we have said, QH over TH plus QC over TC is equals to our Q here for this integral. We have said that is what it is. QH over TC and QC, QH over TC and QC over TC. Now, we are interested in this expression here for work, and we are interested in that expression there for QH. So if we go back here, this, remember, is 0. So what do we have? So what we have here is that minus QH over TH is equals to minus QC over TC. And what is work? Work, definitely here from dq is equals to minus dw, implies that QH plus QT is equals to minus W. So if we put in those quantities there, then we, minus QC plus QC. So if we put in those quantities there, then efficiency therefore will be QH plus QC, QH minus QC over QH, which is 1 minus QC over QH. We need to have that in mind as we want to interface it with this quantity here. So all we need to do now is to rearrange this particular quantity so that we have QC over QH. So we'll have QC over QH, so we can have minus QC over QH is equals to TC over TH. TC over TH. So that we can plug in that in place of QC over QH, that ratio, so that we have the efficiency now is 1 minus temperature of the coal body, of the coal reservoir. It's reservoir at low temperature, but the temperature, the high reservoir. Let's call that our efficiency for the Carnot cycle. That's very important for us to note that. Now, so when we look at these particular processes, we have said that the efficiency of the process is 1 minus TC over TH. That's the efficiency for the Carnot cycle. Now, let us go back again now and also do some additional work. We have said on the saturated liquid and saturated vapor curves, we have saturated liquid, saturated vapor curves, we have 4, step 1, 2, 2 to 3, 3 to 4, 4 to 1, which are now not mentioned because you know each of them, isothermal, adiabatic, isothermal, adiabatic, and so forth. Now, if we go back to our first law of thermodynamics for a steady state flow process, in one of those lectures, which is in the series, we will see that dH plus dC squared over 2 plus d dz is equals to dq minus dw. At this point, I want to mention something. Don't be awfully worried in thermodynamics about negative and positive. Look at the rationalize your answers. Rationalize your answers, because minus or plus are notations in thermodynamics. I just want you to take note of that. They are notations. For example, minus W. In my books, minus W means work has been done by the system, so it's less energetic. It's easy to remember that way. Some people would put work done by the system as plus W. For example, let's say you are the system, and you're in this box. And of course, there's a pulley, and there's this string which you will pull, is going over the pulley, and there's a load here. That's the level, daytime level. So you raise it up, you pull that string, and the load moves up to that level. So we are saying you, the system, you have done work when there's a change in the height of a weight somewhere in the surroundings. And the surroundings has done work when there's a lowering the height of a weight somewhere in the surroundings. And so you can define work done by the system as minus W. You can define it as plus W. The key thing is remain consistent. If your work done by the system is plus W, stick like that. If it is minus W, stick with that. If the heat transferred from the system to the surroundings is minus W, stick to that notation. If you say it is plus W, stick to that notation. That's why it's not awfully important to put too much emphasis on the signs. Look at what is your answer. Is it rational? Is it practical? That's very important. So you have to couple both the manipulations in thermodynamics and the practical reality on the ground when you're giving your answers, because your assumptions could have been that your notations are mixed up and so forth. So minus plus, I repeat, is not critical. Those are notations. They are notations. Now, so in other words, this first law expression for steady state process can be plus or minus dW. Can be plus dW minus dW, depending on the notation you're using. So this second term here is the kinetic energy expression, kinetic energy. The third term here is the potential energy. And in this particular system, these are negligible, so we can assume they're zero. We can assume they're zero, so that dH is equal, and the process adiabatics, dH is also zero, so we can assume that dH is equal to minus dW in a nutshell. So that the work done basically is the difference of the change in the enthalpy for those particular processes. So that when we are talking about efficiency, so when we are talking about efficiency now, which is output, E Carnot modified, will now be the input, the output. This is the turbine, the output, and that is therefore, remember, what is that? The output there is H2 minus H3 minus W inputted on the pump. Remember, that's the pump, and work has to be input into the pump, divided by the work input. That will be H1 minus H2. And for the Rankine cycle, the process is just the same. For the Rankine cycle, the process is the same. The Rankine cycle, the process is the same. We have a saturated vapor curve, saturated liquid curve, and we have our processes. One, two, three, 4, 5. Now, on output or input, again, the efficiency for the Rankine cycle, very simple. Inputted, remember this is the turbine, again. This is the boiler, that's the condenser, that's the pump, and the system. So what do we have? Output from the turbine, that is H2 minus H3 minus the input from the pump divided by, that's the output, divided by the input, which is H5 minus H2. And so those are efficiencies of these processes, of these Carnot and Rankine cyclic processes. And we are going to work in one of the next lectures, we are going to look at several aspects where we now don't just have the enthalpies, we have what are called steam tables. We have steam tables which gives us the saturation pressure table for steam. That is in the steam table, the saturation pressure, saturation temperature table for steam, superheated vapor table, and we have the condensed liquid table. These are in the steam tables. And from these particular quantities, we are going to see, for example, in the next lectures, where we are going to work with these quantities here, in the steam table, it will give us, we will have the enthalpy for the vapor, we will have the enthalpy for the liquid, we are going to have the entropy for the vapor, for the liquid, there's the internal energies and so forth, which we are going to be able to pump and to put into these equations and get actual values when we are calculating. So we are going to look at the pressures. So you read the pressure from the pressure to which you're talking about. For example, if this high pressure here was at, let us say it was 4,000 kilopascals, let's say it's 4,000 kilopascals, and this one here is at 4 kilopascal, because the pressure normally is lower for the condenser. Then you look at the steam table, get the values, pump in and calculate the efficiency of the process. In addition, we are going to calculate from all these matters, we are also going to look at the specific. We are going to look at, let me just denote it as SSP, SSC, specific steam consumption, which is in kilograms per kilowatt hour. That's the consumption of steam in kilogram per kilowatt hour. And we are also going to look at the work ratio, which is total work basically over the work of the turbine. So we are going to do that in the next lecture, where we will use the steam table and actual figures and get the values. So we can stop at that particular point and we continue with our lecture series.